Hello, everyone. Hello, everyone. Good afternoon. Thank you to joining us for this session. Our first presenter is Royce Liu, who is presenting on the Enhancing Seismic Resilience, a pathway to the wider implementation of displacement, dissipative control rocking in bridge. Royce is a bridge engineer working at the Christchurch office of WSP. He has nearly 3 years of industrial experience and 7 years of academic experience. Royce obtained his PhD in earthquake engineering from the University of Canterbury in 2019. Through his thesis titled Multi-Performance Seismic Design of Low-Damage Bridge Piers, Royce specialists cover low-damage seismic design, structural analysis, and the assessment of bridge. He also has interested in soil structure interaction and low embedment carbon design of bridge. Please join me in welcoming Royce.
Thank you, Niku, for the introduction. I'm here in lieu of my colleague Brandon, who was originally going to give this presentation. He gives his apologies due to some unforeseen circumstances. So today I'm presenting on the new low damage design guide utilizing dissipative controlled rocking. It is a team effort. And I'm just one of the co-authors. So we had the University of Canterbury along with WSP working on this, and with people like Alessandro, Ernesto Hernandez, Sabina Piraz, Peter Routledge, Michael Cowan, Brandon McAfee, and myself as contributors. Okay, so just to remind ourselves why we want to have low damage structures for bridges, the most recent earthquake of note that has caused a lot of damage for bridge infrastructure is the Kaikoura earthquake. And as you can see in the photos, with our current design, way of design, you can see that there's some significant damage that can occur from the plastic hinging. Such as potentially bar buckling, maybe fracture, and as well as significant residual displacements. Now, it's important to note that this current design strategy has satisfied life safety. However, there is the cost of downtime and repairs, and at worst, also demolition and construction of a whole new bridge. As well as for some of the structures where not so much damage has occurred, there's uncertainty around the future performance of that structure because we don't know exactly what the strains were in the steel or the concrete, as well as the cyclic life. So that begs the question, is there a better way of achieving capacity design and life safety? And yes, there is. One of those ways is with dissipative controlled rocking. A lot of research on the system has been undertaken worldwide, starting off with buildings, with the press system. And luckily enough, a lot of this research has been undertaken in New Zealand as well, especially at the University of Canterbury. And that means that with the knowledge developed, that has utilised New Zealand design codes, which makes it a bit easier to transfer across into design guides and use here in New Zealand. Now, this system is advantageous compared to plastic hinging because we're limiting the damage into replaceable components, which is the dissipators that can be internal or external. Residual drifts are limited by the unbonded post-tensioning. And any other damage is eliminated by capacity design and or armoring around the rocking joints. I also note that the amount of work undertaken on dissipative controlled rocking had culminated in the construction of the Wigram-Magdala Bridge that uses that technology. Okay. So with how good dissipative controlled rocking is, then you've got to wonder, why don't we see it more in our bridges then? And I'm just comparing here a bit more objectively the plastic hinges against dissipative controlled rocking based on a number of metrics. And you can see that in terms of initial cost, design simplicity, and construction complexity, plastic hinging to date has beaten out dissipative controlled rocking. But with the development of this low damage design guide, we hope to change things a bit. So first up, with regards to design simplicity, a lot of research, as I said, has been done on the system. However, it's all in research papers, and any individual engineer has to go around trying to cobble them together, right? So in this design guide, we bring together everything, so it's basically a state of art, and you don't have to go hunting for things. Moreover, we condensed this knowledge to give simple and clear bridge-specific design advice. And also, we've provided extra guidance around how to implement dissipative controlled rocking with regards to particular design scenarios, such as particular bridge configurations, location, and with regards to seismic hazard, and ground conditions. With regards to initial cost, we hope to also get an edge on plastic hinging by giving advice around how to change the way we are utilizing the limit states with regards to designing for DCR. As it is a low damage system, it means that it's basically repairable all the way up to a collapse avoidance limit state, and I'll explain that point a little bit further on in this presentation. And lastly, with all this information at hand for the design engineer, we then hope to see more of the system being designed, which means that more of the system will be constructed, and hence, as contractors become more familiar, then their sense of the complexity of the system will reduce, thereby reducing the sense of construction complexity. In terms of what the design guide actually looks like, this is the front cover. It's completed in its first draft and ready for peer review. There is talk about putting together some worked examples. So that is covering the design of particular bridge structural configurations using this system. And there's also the possibility of inclusion of all of this information or reference to it in the bridge manual. Some key elements covered by this guide are the detailing and design of the structural elements that make up dissipative controlled rocking, so the dissipators, the post-tensioning, the armoring. There's also an explanation for how to apply force-based design and displacement-based design to DCR. I will note that displacement-based design lends itself way better because you can, dissipative controlled rocking is limited by the strains that the materials and components reach. We also provide a simplified moment rotation calculation procedure for section analysis, as well as further guidance on other types of analysis as well, if you needed something more advanced, lump plasticity, Winkler springs, that sort of thing. Another important part of the guide is an explanation for the pathway to compliance, as dissipative controlled rocking is an alternative system to plastic hinging. And lastly, it also provides an outline of opportunities for future developments. There's always new things to learn and some current unknowns. So in terms of some reasoning for why we need a separate low damage design guide, compared to buildings, and also some separate details that it covers. Firstly, bridges have minimal non-structural elements, and any non-structural elements on it, such as pipes or barriers, will only really get affected at any movement joints and would only need to be really detailed across those joints. Bridge repair, thus, is directly related to the severity of damage of the structure itself, rather than the non-structural components, another difference to buildings. The displacement-based design of bridges is similar to that of buildings, but as there's not any non-structural components, then displacement limits don't make as much sense, and you have strain limits governing. And then lastly, the bridge manual requires explicit checks at the collapse avoidance limit state on top of the damage control limit state, which for the buildings people is basically ultimate limit state. And there's in the bridge manual the clear definition of the expectations of CALs, as well as the demands to use to check that. Some other reasoning for having a low damage design guide is because it doesn't, low damage design doesn't quite fit in well with the current seismic design framework, which is centered around life safety, which is an absolute. However, the point of design is actually below the collapse point, the ultimate limit state. And then we're relying on having a buffer between that and the true collapse point of the structure, which is provided through robustness and detailing in order to provide that. And so what that effectively means currently is that we design to DCLS and then we just do some checks for the collapse avoidance limit state as well as the serviceability limit state and rely on that detailing to get us through. So just focusing in on that point a bit more and contrasting the differences in terms of repairability. So this is, say, the pushover curve of a plastic hinging bridge column. We design it to the ultimate limit state, damage control. Below that point, the structure can be considered to be repairable. It meets all the requirements of damage control limit state. It's in the name. But then beyond that, then it can be deemed unrepairable because there's more uncertainty around what the damage state, exact damage state will be. So there's the possibility for bar buckling. There's the possibility of severe concrete crushing within the core. Unlike dissipative controlled rocking, where we have basically dissipators to worry about and the post-tensioning, if we were to do the design the same as that for plastic hinges at the damage control limit state, it would be limited by the strain set there. Below that point, the structure is counted as repairable because all you do is replace the dissipator. But interestingly enough, past that point, up to yielding of the post-tensioning, it's also repairable as well because the same thing, you just replace the dissipator. So what that means is that you can satisfy the damage limit, the control limit state requirements all the way up to the collapse avoidance limit state. And that means that some of the strain limits that we have at the damage control limit state don't make as much sense in limiting our design. So in this design guide, we sort of redefine a way of applying design to dissipative controlled rocking. We still have life safety as the focus. However, we make the main design point our collapse avoidance limit state now. And then we detail for repairability all the way up to that point. And then we only need to do some checks at the damage control limit state to make sure we still meet some requirements there with regards to like low cycle fatigue and the likes. And so then the whole way of design changes to being centered around collapse avoidance limit state because we know what the mode of collapse would be. However, we do add in some requirements that such a system would need to meet in order to design in this way. Such caveats include that the rest of the structure needs to be undamaged in the earthquake, and any components that need to be repairable or replaceable can be repaired or replaced all the way up to the collapse avoidance limit state. That the serviceability limit states are still met so that functionality is not compromised. That there's no cyclic degradation or softening of our structure up to the collapse avoidance limit state, because we don't want to have any uncertainty in the response of our structure, which will change everything. Residual drift is minimized. And lastly, that articulation and all other relevant details need to be designed to still facilitate the expected structural displacements. So in terms of what that means really for a dissipative controlled rocking column designed to CALS first and then checked at damage control limit state, consider these two pushover curves, where the top light grey one is for one that has been designed to the damage control limit state, where it's limited by 5% strain in the dissipator, and compared to the one below, which has been designed for the yielding of the post-tensioning at the collapse avoidance limit state. You can see that basically it allows a reduction in the base shear that we need to design to at the expense of greater displacements. But as I explained before, displacements don't matter so much for bridges, because there's not any non-structural components that are so sensitive to that. And what that means is that potentially we could have some significant savings for construction, especially for the foundations, by designing to lower forces. And this can make a low damage system such as dissipative controlled rocking more competitive than plastic hinging in that sense. We also provide some guidance on when to consider dissipative controlled rocking in our bridges. So the bridge manual asks us to consider low damage design for bridges of importance level 3 and higher. However, it doesn't provide any guidance on how to go through that consideration. In this guide, we do provide that. So firstly, dissipative controlled rocking would be beneficial where the bridges are of high importance and there's high seismicity. It lends itself very well to being used with precast construction, because all the rocking joints means you have like individual members that are just connected together with post-tensioning and some dissipators, right? It doesn't it needs to be used where the ground will not be too soft, because we want to avoid having the flexibility of the rest of the structure taking away from the gap opening at the rocking joints. And also we provide some guidance around what sort of structural configurations dissipative controlled rocking would lend itself well to, which is basically those where the joints would be easily accessible, which is basically the same as the structural configurations that the bridge manual allows us to design for high levels of displacement ductility. I'll just note that a lot of those structural configurations there aren't widely used in New Zealand. So we also speak a bit about how it should be used in, say, a 2-column bent, which is much more common in New Zealand. So we suggest to have the dissipative controlled rocking connection at the top of the columns, and that also gives you the opportunity to use precast cap beams, which would also lend well with a precast superstructure. We do note that if there is any in-the-ground hinging, that needs to be checked, and the amount of displacement ductility demands required there needs to be minimized. Otherwise, the structure's not going to be as low damage as you think. Cool. So in conclusion, plastic hinges are a perfectly viable way of resisting seismic demands, but there's room for improvement, as you had seen from my example with the Kaikoura earthquake. Collaboration between research and industry has led to the implementation of dissipative controlled rocking on the Wigram Magdala Bridge. That's had taken a number of years. And then following on that, then we've been able to produce this design guide. We need to consider alternatives to plastic hinges and have a rethink about how we can apply the limit state design to such systems. As I had shown in my example, with dissipative controlled rocking, it's repairable all the way up to the collapse avoidance limit state. So why not just design to that point first? And with bridges, the displacements don't matter so much, so you could also allow the displacements to be a bit higher, reducing some of the base shear and hence foundation costs. And lastly, there are practical opportunities to consider alternatives such as dissipative controlled rocking, and this design guide hopes to help enable that and similar systems. There's much more to be covered in this guide, so watch this space. Thank you.
Thank you so much for your great presentation. It's very amazing. We have a time for about 5 minutes for question. Is there any question on the floor? Yeah, Ali?
In the guide, you mean?
In general design, I mean, I'm just saying that, I mean, you have a low damage system that you have added to the pier in terms of the allowing for rocking system, but does this we need to detail the pier even more severely to allow for the low damage system? And
so you would just follow capacity design principles there. In terms of what sort of performance level you want, that will dictate how much detailing you want to implement, right? So if you wanted absolutely no damage, completely armored, that will cost a bit more than, say, having internal dissipators where you have the replaceable dissipators, but let's say less armoring, but a lot more stirrups, so that you have a zone of concrete that you are going to fix up afterwards, but it's in that defined zone.
okay,
So, yeah.
thanks so much.
Hello, Thailand here. Do you think the rotation capacity needs to be considered again for the bearings used between the piers and the superstructure when we have these low damage design? Because the bearing should try to take the same rotation that this is allowing.
Good question. So that's a displacement compatibility question. I would argue that the rotation, rotational demand should be the same as that for plastic hinging, right? The only difference is how that has been distributed. So with a rocking joint, it happens at the joint and the member stays, just has the flexural deformation. Whereas with a plastic hinge, it's distributed over the plastic hinge length, right? But you still have the same angle at the end, plus the flexural deformation. So it should be the same. If you have a 2-column bent, then you don't need to worry about rotation at all. So I guess your question would be more applicable for single-column hammerheads type bridges.
Thank you so much, Royce, again for your insightful and very amazing presentation. So much. Please join me to take my photographs. Our next speaker is Moustafa Al-Ani, who is presenting on the place of base isolation and other mechanisms for mitigating significant seismic hazard risks in bridges. Moustafa is the lead advisor structure at the New Zealand Transport Agency. He completed his PhD at the University of Auckland, and his experience spans across design, assessment, and research for bridge in particular and structures in general. He has experience working with codes from New Zealand, Australia, US, Canada, and Europe. His research interests including the analysis and design of seismically isolated bridge structure for earthquake resilience using a variety of earthquake protection systems and the design of the bridge structure to variety of international design code. Moustafa is also committed to contribution to advancement of the engineering industry through the presentation of industry seminar and involving in professional organization. He is currently president of the Concrete New Zealand Learning Society, is New Zealand head delegate for FIB, and has ongoing involvement in technical activity within FIB, IABSE, and the TRB. So please join me to welcoming Dr. Al-Ani. Thank you so much.
Thanks, Niku. I probably should have cut that bio down. Sorry about that. All right, so I think that was a long enough introduction. I don't need to introduce myself again, but I am going to start with a disclaimer. I've gone slightly off-piste. You were promised a lot of base isolation, and when I saw I had most of half an hour to talk, I didn't think I could talk about base isolation or bridges for half an hour because it's been around for over 50 years, although I'm now informed it's unproven technology as of yesterday. I have apologized to Sabina already about that this morning, so instead I will talk about base isolation for a bit later on, but I will also share some of the other challenges we're facing with seismic design of bridges in New Zealand. So just like buildings, bridges and transport infrastructure in general has faced a lot of challenges in terms of dealing with earthquakes over time, whether that's a century ago or a decade ago, or a decade or so ago. So in terms of the history of bridge design, we've largely mirrored the building space until the 2000s, with a few exceptions over time. So there's some there, I won't run through them all, but we see things like seismic detailing coming in pretty early on. You see importance factors introduced in the early 70s, and the beginnings of things like soil structure interaction also starting to come in. And then you see things like ductility being detailed for, more focus on foundation design, and 3 levels of performance, so SLS and ULS, or DCLS as we're used to, but also collapse avoidance, coming in pretty early in 1987. And since then, the bridge manual, as it then became in 1994, has evolved, and I'd say pretty rapidly over that time. So where you've got a lot of focus on liquefaction as a result of the Christchurch earthquakes in particular, but even before that, a lot of focus on soil structure interaction, and then the bringing in things like near fault effects and fault movements. So this is where I kind of throw in my second disclaimer. I have motivation behind running you through some of this and what I'm going to run through in the next 10 minutes or so. And that's because I know that a lot of the people in this room aren't bridge engineers and aren't familiar with how we operate in the bridge space. So I figure if I give you the context of the space we operate in, you might appreciate the challenges more and might be able to come up with some smart solutions or help us come up with them as well. Basically, everything we do in the bridge space is an alternative solution. There is no B1 VM1 solution for bridges. We're definitely not heading anywhere near that direction anytime soon. So that's kind of first thing to understand. That means that most designers rely on the NZTA bridge manual. It's got a long history. It is technically written to be used for state highway bridges, but I think I've found it's used for almost all bridges in New Zealand, as well as some non-bridge structures. It refers to a number of national and international standards. In some spaces, it's more almost like a Rolodex. It just points to other standards like 3101 and 3404 that you're familiar with, but also AS5100, AASHTO, LRFD Guide, British standards, and the Eurocode. That being said, the seismic design section in the bridge manual is almost completely standalone. It does point to 1170 for some things, but apart from that, not much else. What it does have in it is still got the 3 design levels, and we'll come back to those in a bit, when we start talking about challenges. But you still see your SLS, DCLS, and collapse avoidance limit states there. It also illustrates just kind of how rapidly it has evolved to move with the times, because it does allow for multiple events, so aftershocks, which was essentially a reaction to the Canterbury earthquake sequence. It also has a strong focus on kinematic effects and ground movements, including design scenarios of how you might incorporate those with inertia. I guess one takeaway from that is because it's evolved so quickly, we've kind of tried to keep that going. So late last year, there was a technical advice notice published that basically pointed to the 2022 National Seismic Hazard Model. Now, that might seem a bit radical, but the reality is it was actually plugging some inconsistencies, because for the vast majority of, at least of the, if you measure it by spend, vast majority of NZTA projects, we were already doing site-specific studies. So one way of looking at it is actually making sure we're accepting and consistent science in the design that we're applying. I won't go through that in detail, but what it does say that is worth highlighting is that a comprehensive review of current seismic design procedures in the bridge manual and associated technical documents is underway. This review encompasses seismic risk settings and associated performance criteria. So that just hints to the fact that there is a big job ahead of us, and that's some of what I'm alluding to in my presentation today. I'm not going to waste your time telling you that New Zealand's pretty seismically challenged, or most of New Zealand is anyway. We've got high seismicity, we've got soft soils, we've got ground instability, fairly young geology, and active faults riddled throughout most of both islands. What I will point to, though, is when we go back to our 3 limit states, is if you look at our collapse avoidance limit state, or if you look at actually our definition of our limit states first, you'll see that there's a clause in there that says, you probably can't, I'm not sure if everyone can read that, but it says, the highlighted section there says, bridges with a construction cost including associated ground improvements exceeding $18 million are IL4 structures. We don't actually get many bridges for less than that these days, so that's actually a lot of our bridges if you take the bridge manual at face value, which lands us at a ULS or DCLS of 2,500 year return periods, and then we go ahead and amplify that by 1.5 to get to our collapse avoidance. Now, if you kind of take what Royce mentioned earlier about you design for DCLS and then kind of rely on things to cover for collapse avoidance, that's true on a structural level. Ground performance is different, because we still are checking for ground performance at that collapse avoidance limit state, and there are big step changes that happen when you look at how the ground behaves. And just to put an even finer point on it, if you look at this is just a pure, simple output from the current NSHM, 1.5 times a 2,500 year return period in Wellington for 300 meters per second VS30 gets us almost 10,000 year return period. It varies around the country. It's somewhere between 5 and 10,000. Here it almost perfectly maps onto the 10,000 year return period. That's a pretty high standard to set for almost all of our bridges. Other challenges that we're facing, so with hazard definition, we know that our understanding of the seismic hazard is evolving over time. That's why we have new hazard maps being published. But actually, even just defining the hazard needs a bit more work in some spaces. A key example for us is actually vertical spectra, where we're seeing some excessive vertical accelerations. They may be true, but they're not. I think there needs to be more work done to justify those. The combination of inertia and kinematic effects, and this is probably a good time to say that we're not unique in a lot of this. I know we pretend we are. I spent a lot of time in the last 12 months talking to the likes, to our equivalents overseas, the likes of Caltrains and Federal Highways and others around the world. Caltrains are particularly interested in this. They are behind what we're doing. Well, we do more than they do. I don't know if they're behind. We do a lot more than they do. And when we look around the world, no one else has gone as far as we have in this space yet. And fault movements would be a similar space, where we're seeing kind of fault movements in the order of 5 to 10 meters horizontally and up to 5 meters vertically. Designing a bridge to span that can be challenging. Ask Caltrans, they're trying to do the same with their high-speed rail. Multi-hazard resilience kind of speaks for itself. We have a lot of geohazards that interface with the performance of our bridges. I mean, and probably my third disclaimer in this presentation already, the top photo you probably recognize isn't actually from an earthquake. It's from Cyclone Gabriel 2 or 3 years ago now, but still a good illustration of the geohazard that we face. And I won't spend too much time on this. This is just to say kind of the theme of the conference, I guess, embrace or harnessing uncertainty. Uncertainty is an aspect that we haven't really addressed properly in how we design for structures, because what I've shown here is, again, an output from the NSHM, but encompassed within the bounds of uncertainty of one is all of another location. So we know a lot more about some locations than we do others, if you look at the uncertainty that's associated with those. I am getting to some base isolation talk eventually, I promise. How do we tackle these challenges? So I guess the first step is actually let's step back and look at the definition of resilience, or the 4 Rs as we now kind of like to talk. So at a transport network level, that's risk reduction, that's readiness, that's response, and that's recovery. All great terms. There are a lot of R words we could use here. Not that useful when you sit down and design a structure. So at a structure level, you may have seen curves like this that talk about robustness, redundancy, resourcefulness and rapidity, or other different versions of those words. I think that those are good principles to try and kind of get to when we talk about how we design. So in my view, a lot of traditional low damage design options actually primarily focus on that first drop, the robustness, right? And I think we need to think wider than that, and that's kind of alluded to without any more detailed guidance in the technical advice notice I mentioned earlier. So you see phrases like design solutions that kind of embrace or enable fast repairs, minimize network disruption. You see things like performance-based criteria being a key focus, particularly when it comes to settlements, ground performance, and the impact on structures. And it also points to opportunities for efficiency. So identify where the step changes happen in the performance of the structure and work around those. And I think it kind of goes back to an answer that Hamish gave at this afternoon's presentation about, or his Q&A session this afternoon, of work out what the structure or the location kind of leans towards in terms of the step changes and those efficiencies and performance. And you embrace those as a starting point. And then the other thing it points to is adoption of low damage solutions, and that's probably a good segue into base isolation. and low damage design. So I'd say New Zealand has historically been at the leading edge of these things. So you can't get away from some of the early examples that are up on the screen there in both buildings and bridges spaces. And even more recently, things like press and Royce's presentation on the DCR being applied on Wigram Magdala are key examples of just how quickly New Zealand can kind of implement new innovative solutions. That being said, we don't see many base isolated bridges in New Zealand. There are reasons for that, but one of the key reasons we believe is that A, there's no standard for base isolation in New Zealand, and there's very little guidance, especially when it comes to base isolation of bridges. And this is where Concrete New Zealand Learning Society and the NZTA stepped in and co-funded this project. Probably the meatier chunk of work is that what Royce presented on. Part B of that work is actually a guide for base isolation of bridges. The scope of that was kind of to develop a design framework that fit within the New Zealand design framework we already have. Not reinvent the wheel, take what's already out there as much as we can from the likes of AASHTO and Eurocode. And then there may be a phase 2, hopefully, in the future for worked examples and webinars and the like. Quick run through of kind of what base isolation is. I think a lot of people in the room will already know this. It takes a contrarian view to how you might design a structure. Instead of increasing your capacity, you reduce your demand. In the case of bridges, that's putting isolation bearings at the top of the columns traditionally, at the top of and just below the deck. That gives you the period shift that you want to reduce your accelerations, increase the displacements, and also gives you the increased damping that you're after to dampen both accelerations and displacements. Which gives you a design trade-off in terms of accelerations versus displacements. The three kind of guiding principles that we generally adopt for isolation, at least of bridges, is maintain horizontal rigidity during service, so you don't want it to be flopping around during when a big truck breaks or under minor events. But during shaking, you want low stiffness and some energy dissipation. And post-earthquake, you want it to have enough lateral restoring force to mostly bring it back to where it was before. Some of the things that the guide that's currently in draft does go through are some of the analysis methods. So first up are some fairly simple static methods and some guidance on more advanced analytical dynamic methods. So it presents the single degree of freedom kind of simplified method, which is very basic, can be done on a spreadsheet fairly easily, requires 2 or 3 iterations generally, and gives you a pretty good answer for, at least for prelim design level, for the vast majority of bridges. So to do that, you assume a deck displacement, you calculate effective isolator stiffness and then associated effective substructure properties, you calculate effective system properties, so your period, your damping, and then use that to calculate a new displacement, and you iterate on that. Bridges being fairly well constrained to single degree of freedom systems in most cases are very well amenable to that kind of approach. There have been studies that show actually this method is less than ideal for when you have relatively heavy substructures. So if you've got hammerhead piers where the weight of the pier cap is actually approaching a decent enough ratio of the weight of your deck, or other ratios of stiffness ratios, you might actually not get decent answers out of the simplified method. So presented in there is also a 2 degree of freedom method. It follows the same general approach, it just breaks it out into two modes, and they're actually, again, it's a fairly simple method that can be implemented in a spreadsheet. The guide also provides guidance for more detailed analyses. So once you get into detailed design rather than prelim design, you might turn to things like response spectrum analyses, and it provides guidance on modeling and how you might develop your hybrid response spectrum, as well as combination of modal responses and things like that. As well, and it provides guidance for time history analyses, so again, modeling, selection and scaling of ground motion records, and assessment of response parameters. It also goes through step by step how you might design some of these bearings. So it focuses on lead rubber bearings and friction pendulums. Should clarify single pendulums. I know there are triple pendulums out there, but that's not covered in the guide at this stage. So it's suitable enough for prelim sizing of these bearings. It's probably suitable enough for detailed design sizing, but generally your manufacturer or supplier will actually do a lot of that with you as well as a designer. It also includes guidance on sensitivity analyses, so to account for variation and tolerance, to account for aging and environmental effects, as well as heating and scragging effects, particularly for rubber bearings. It gives some fairly, I'd say obvious, but fairly simple guidance on design of force-controlled elements, so essentially capacity design, some guidance on constructability and detailing, Q&A and testing procedures, as well as operation and maintenance requirements that might be worth considering. What's not covered in there, and I've said in here probably needed, I think it would be nice if it's covered somewhere, and so that might be a further piece of work in the future, is how you might combine, again, kinematic effects with this design of base isolated bridges. And that includes ground movements as well as fault ruptures, things like that. Setting performance criteria in accordance with wider performance, so that's kind of alluding back to our definition of resilience and the 4 Rs and looking at the full curve. We need to acknowledge, just like with DCR, with base isolation, it's a different beast and it requires different thinking than what our plastic hinge kind of conditioned framework already allows for. And some guidance on efficiency of isolation in New Zealand conditions. And the reason I say that is because period shift is a big advantage of base isolation. A lot of our sites are already on very soft soils where your period is actually already pretty long, or can be. And so where is it best to actually chase these opportunities? So similar to the DCR guide, the base isolation guide is currently in draft form, or final draft form. So the next piece of the puzzle is a peer review as well as alignment with other guidance and standards that are being developed. So the likes of NZSEE's guidance on base isolation. It will be published once finished as an NZTA/Concrete New Zealand Learners Society guidance document, and hopefully worked examples and a seminar or webinar series would follow. And I think I'm okay for time for 2 more minutes. So what else are we, as in the NZTA? I wear a couple of different hats here, so with the NZTA hat back on. What else are we doing? So we are working closer with other agencies than I think we had in the recent past, and I believe that was kind of raised as a question at a presentation yesterday that I'd missed. So we are talking to the likes of MBIE and NHC, but we're also talking to Caltrans and the Federal Highways and a few others who are leading some relevant work overseas. I've kind of slightly cheekily put in here re-engaging with technical societies and universities. If you look at, say, the DCR work and that being applied on Wigram Magdala, that's a key example of the power of asset owners working with, especially central asset owners working with research institutions and with consultants all together. And I think that's something that we need to get back to doing. Reviewing design framework and risk settings, and I'll touch on that a bit more later. So let's come back to that. And we're also, we have a piece of work looking at what international standards are doing. As I kind of alluded to, I actually think we're ahead of, or we do a lot more than some of the other international standards do in this space. So it's a bit of a balancing act as to how we follow their path. And I will speak to a couple of the other points if I have time. So review of risk settings. If you were here yesterday and you saw the presentation that was talking about where 1170 might be heading in terms of importance levels, makes my life easier that was yesterday because I can then point to it. And we need to follow a similar path in the bridges space, but probably a parallel path. What you see here, if you're not familiar with it, is the kind of annualized fatality risk kind of metrics that are often used in the building space. They're not necessarily appropriate. I don't believe they're necessarily appropriate for bridges. The fatality risk on a bridge isn't necessarily the most, it's very important, but it doesn't need to be treated in the same way as it is for buildings. And then when we do that review, it's also important to acknowledge just what Royce has already mentioned, what I've mentioned earlier around how do we have a framework that actually acknowledges and respects the place of low damage design in setting performance criteria and setting and the advantages of those systems, right? So I don't believe we currently have that in the bridge space. Oh, that's already been. And just a couple of other, one other final thing that we are doing is scenario planning. So this is a cross-government agency piece of work. So if you're not familiar with it, the AF8 is a major identified hazard, so a magnitude 8 earthquake on the Alpine Fault. So we are going through and actually identifying what that means for the state highway network around that part of the country and what a response would actually look like to that. Doesn't mean we can go and replace all the bridges that are identified as at risk, but there might be other ways that you would address that risk. And a similar piece of work coming further down the line on the Hikurangi subduction zone. Thank you.
Thank you, Moustafa, for great presentation. We have time to the one question, and then I just mentioned that we have at the end of the session 10 minutes for the question again from all of the three presenters. Any question on the floor? John.
Thanks for that, Moustafa. That was really great. I think it made me feel happy to be a building person because it strikes me that the vagaries of nature make your job harder than mine. But one thing that, I see that when we start talking about return periods and so on, your annual probabilities of exceedance are even harder than ours, and we start to chase higher and higher and higher loads. And it does strike me as a bit futile at times. Often, if I think about what happened at Kaikoura, even if we had our structures designed for that level, the entire network was taken out by things beyond our control. There's thought being given to, maybe we rather than focus on single elements within the system, we focus on broadening the network so that we have more system redundancy across the different branches of the network. Would that be an alternative solution to just chasing the loads up, do you think?
Short answer is absolutely yes. The slightly longer answer is that kind of leads to what I was alluding to with following a similar but parallel path to the work that MBIE is doing in terms of updating 1170, because the network effect for a transport network needs to be considered, and that thinking is not currently even alluded to really in the bridge manual and our current design framework. So we need to do a lot of work to enable that and say, what does failure of this single bridge mean for the network? Is it a bridge spanning a waterway and you have no other way across there? Then yes, we should invest more money on that bridge. Is it one of a multitude, or is it a bridge that there are detours around fairly easily, at-grade detours in particular, where you don't actually crossing any other bridges? Then maybe we can allow a bit more damage on that kind of structure.
There is one question from Ken. Are you able to compare the bridge-based isolation guidance and the draft guidance for building? Are there the key difference?
I had an email from Dion, I think while I was overseas, saying we should catch up, and we still haven't caught up. So short answer is, haven't got there yet, Ken. We will get there. I do need to sit down and compare line for line. Well, yeah.
Thank you again, Moustafa, for your great presentation. Please join me. Thank you. The next speaker is Hamish McKenzie, who is presenting on the MBIE NZSEE SESOC low damage seismic design guidance. Hamish is a principal at Holmes with over 28 years of experience as a consultant structural engineer, and the last 18 years based in Wellington. Hamish has been involved in a multitude of structural design, earthquake engineering, seismic assessment, and adaptive reuse projects during his career, including many well-known buildings in Wellington. Please join me in welcoming Hamish for the presentation. Thank you.
Thank you, Niku. So, look, I think I need to start today with a few disclaimers and some acknowledgements. This is intended to be a very brief update around kind of status and progress of the low damage seismic design guidance document. Some of the background: this document's been around for a long time in terms of its development, and it's progressed in some fits and starts over the last 10 years. The most recent piece of effort to get it across the line has only really been happening since sort of mid-October last year, so it's been a reasonably short sprint at the end of last year to get the technical guidance developed to a draft state, and so I'll talk about that a bit today. As part of this also, this is a brief update. I'm not going to get into any technical detail, but Stu Oliver is putting together a paper and is going to make a presentation at the SESOC conference later in the year, and he's going to dive into the detail in a little bit more detail. So those who are more interested in understanding how the guideline will be applied and how to use it in a bit more detail should keep an eye out for Stu's presentations later in the year. I also want to make a couple of acknowledgements to a couple of people in particular. Jess Court-Patience, who's previously been our project manager and has done a great job of corralling the project team on this project. Jess has more recently been away on a period of maternity leave, but she has been very instrumental through the back half of 2023 and into 2024, helping us get together a detailed project plan, a scope of work, and putting a funding application into NHC to get this project off the ground. And she's worked closely with Stu in doing that as well. So really wanted to acknowledge the work that Jess had done to get this off the ground and make it a reality. And finally, just wanted to thank both Ken Elwood and Caleb Dunn from MBIE and NHC respectively. They've put a lot of passion and commitment and effort into getting this off the ground, so without their ongoing support this wouldn't be happening. So to get into this in a little bit of detail, and thinking about the structure of the low damage seismic design guidance series, we've split it up into 3 volumes. Volume 1, the client guidance and client-facing document, has been developed by MBIE and resilient organisations, so Charlotte Brown and her team have been instrumental in that. Volume 2 is the performance framework piece, and that's been developed by MBIE and led by Dave Brunson at Kestrel Group. And then the Volume 3, the technical guidance piece, which is the sort of bulky and more weighty document around how to implement low damage seismic design, has been developed via SESOC and an MOU with NHC and funding through NHC. So it's been split into various component parts. And a little bit more detail on each of those component parts. So Volume 1 introduces the benefit of low damage seismic design and what it means for developers, owners and tenants. And that's actually been published and it's released, and you can find it on the MBIE website. So if you do a Google search for LDSD and MBIE, you'll be able to find that document there, and it's, go and have a look for it, and it's available for use. The performance framework, the Volume 2, defines the hierarchy and interrelationships between the overall outcome objectives and the corresponding performance goals and physical states. And that's been developed in part and in draft and somewhat in parallel with the Volume 3 technical guidance, and it's proposed to be released later in the year. And then the Volume 3 piece, which is the more weighty technical guidance document on how to achieve low damage seismic design from project establishment and preliminary design through to developing engineering and design criteria and then implementing that through developed detailed design and into procurement, construction and post-construction phases, has been developed in draft, and it's been submitted to peer reviewers, and we've had a really productive peer review phase, just been happening in the last 3 months. We've got some great feedback from the peer reviewers, and the project team is just working its way through the volume of peer review input to get a second draft prepared for the client team and to take the guidance document through to release again later on the year. And there will likely be the opportunity for a second draft to be released to certain parts of the industry for a bit more broader comment and input later on in the year. So a little bit on each of the volumes and how they work together. So Volume 1 is about the who and who is LDSD for and how they can seek the benefits from a low damage seismic design approach. It also gets into the why, so why should clients, owners and tenants want to go beyond a building code minimum approach, and it helps determine client needs, priorities, and provide some commentary on the benefits. And it starts an initial conversation around the how, how should clients go about setting up a design team, thinking about the briefing process, and a little bit on how clients and design teams kind of might get underway. And I wanted to bring this slide up, and not that you'll be able to read the detail, but this is a project briefing sheet that's contained in the Volume 1 that's already been released. And it starts to set up a whole bunch of questions that design teams might want to be asking clients around their needs and priorities for a building and building development that can help tease out whether a low damage seismic design approach is appropriate for a given building, a given owner, or a given building use. Onto the Volume 2, the performance goals, and the guideline sets up two specific performance goals, the first one being damage control, and then the next one being improved functionality. And so alongside that, the guideline has set up 3 low damage design levels, imaginatively called Level 1, Level 2, and Level 3. And Level 1 can be categorised as a thoughtful code-compliant building, so it doesn't impose any specific damage control limit state expectations, but it just requires a few key issues to be thought about in a little bit more detail than a standard building code minimum design, specifically around seismic hazard, and with the likelihood of adopting the TS when it's issued, around non-structural elements to be designed in accordance with the BIP Code of Practice, some more restrictive ULS drift limits to make sure we've got slightly stiffer buildings with lower levels of ductility, and thinking about capacity design and tighter regularity constraints for the primary structure in a similar way to the Design for Uncertainty document that NZSEE released a couple of years ago has outlined. And then the level 2 and level 3 low damage seismic design categories do impose damage control limit state expectation at 2 distinct annual probability of exceedance levels, and those requirements have been calibrated through some work done by Tim Sullivan and his team at Canterbury University to some loss predictions, so that there is some level of calibration to some expected losses if those performance levels are achieved. In terms of improved functionality, the Volume 2 document has outlined a series of operational stages from safe egress only through to full functionality, and has landed on a partial functionality performance goal to be appropriate for a low damage seismic design outcome. So it's not about absolutely no damage and full functionality, but thinking about the idea of a partially functional building that can be up and used reasonably quickly, but that specific elements or specific functions of the building might take a little bit longer to restore to full functionality. Overall, the document basis is sort of centred around some of the learnings from recent earthquakes, and a number of those learnings have been discussed here over the last couple of days as well, so there might be a couple of more data points we can add to the list. Around the notion that we've consistently seen that stiff, regular buildings on good ground perform well in earthquakes, provided the secondary and non-structural elements are all tied together adequately. And so the document kind of focuses attention on limiting building displacements as an effective means to mitigate damage to the primary structure and deformation-sensitive secondary components. That's not to say that is always the only way to achieve a low damage seismic design outcome, and the document's going to be flexible enough to allow designers to think about other ways of achieving a similar outcome, but there might be a little bit more thought needed there by those design teams in terms of the calibrating the losses that a more flexible structure might deliver to ensure that a similar performance outcome is achieved. And just touching briefly on the document structure, it's set up in a number of sections, or at least the draft document is, and this is all subject to change and following peer review input. But the first 3 sections around introduction, how to achieve it, and then the design and briefing process really focuses on design teams doing their job well, collaborating effectively together, and a holistic view of the building. It's purposefully not about structural engineering and structural design sort of driving this, a focus on kind of lead designer input, regularity, and the like, and we've had really good input in developing those sections with Michael Davis from Studio Pacific Architects, and that's sort of come through in the document, and hopefully some helpful tools to enable design team to kind of work through the expectations of the guideline. Section 4 is obviously on seismic hazard, and then Section 5 gets into some of the more substantive parts of the document around specific component design, so foundations, primary structure, building envelope, building services, vertical reticulation or vertical transportation, and stepping through on a component by component basis the expectations of low damage seismic design. Section 6 looks specifically at the level 1 type buildings, and there's suggestion we might rearrange that a little bit to give that more emphasis earlier in the document. And then Section 7 focuses on the post-design parts of the design process, procurement, construction, and post-construction, recognising the vital importance of those stages of a project to ensure a building can achieve a low damage outcome and be up and usable, soon after an earthquake event. The document also has a raft of appendices, and I wasn't going to go through these in any detail other than to talk briefly to Appendix 3 around industry research needs, and a clear observation through the development of this document is there is lots of gaps in the research around kind of low damage outcomes and the calibration of certain parts of building systems in terms of damage avoidance. And so there's a section and quite a detailed list of possible research needs that would enhance the use and the level of certainty around some of the principles that we're trying to achieve. The document also leans pretty heavily on some other recent documents in the industry, so we're trying to avoid reinventing the wheel and leaning on the likes of the BIP Code of Practice for non-structural elements, the recent geotech modules, the seismic hazard parts of the TES, and also guidelines that have been produced by other government agencies, this one being Health New Zealand's design guidance note that was issued in the last wee while, but also Ministry of Education's requirements document as well has come into play as we've developed this. And finally, this all couldn't have been done without a team of cross-discipline specialists. So, a big shout out to those people. We put this diagram together a few years ago, and it's got the old EQC logo. So that's obviously been one change through the process. But otherwise, the project teams remain reasonably consistent, with a few minor role tweaks here and there. But wanted to specifically recognise Jess, and then Simon has taken over from Jess to help corral all the various parties in recent times. Stu as Editor-in-Chief, and then the discipline leads, Martin Weems on Building Services, Michael Davis, Architecture, Paul Campbell has provided some really useful input to certain sections, Stu obviously as Editor-in-Chief and Structural Lead, and Stuart Palmer has swapped over with Luke Story, so Luke Story from TNT has led the geotech aspects of the development, plus very valuable input from others around fire, facade, loss and downtime, non-structural, etc. So look, that's where we're at. Volume 1's out and available, so go and have a look for that. It was referenced by Charlotte earlier in the day as well, so good to get a few mentions of that during the conference. And as I say, Volume 2 is prepared in part and in draft, and Volume 3 as in draft has gone through a peer review process, and the project team's working its way through that with a view to get that out to all of you later in 2025. Thank you.
Thank you, Hamish, for your great presentation. Now we have 10 minutes for QA for all of the presenter. Any question from the floor? We have one question here. So Karen asked that, will there be some translation of LDSD definition and proposed TS definition, such as the levels versus FCI, SC1, or will they intend to keep it separate?
I suppose the quick answer on that is I don't necessarily know, given some of those TS definitions I saw for the first time yesterday, so there's probably a bit of work for the team to go through as we understand the broader TS and as it gets published and comes out to the industry, to see how some of that sort of work flows back into the low damage seismic design guideline. Primarily, you know, we'll seek to keep those aligned as best we can, but there's a bit of a chicken and egg thing going on there of which comes first.
Any question? Yep.
Hamish, thank you for the presentation. You mentioned something about limiting deformation to try to limit damage. So how much? How much do you recommend the deformation is limited?
I'm probably not best to discuss that. I might pass that over to Stu, but Stu's going to provide a bunch more detail around that as part of his SESOC paper in the SESOC conference. And suffice to say, that's an area of ongoing research need, depending on what components we're trying to protect damage of. So that's been an area that the project team's been grappling with. Stu, do you want to provide any more detail on the specifics?
Yeah, so I guess there's kind of 3 different ways you can do it, and one's called the prescriptive way, which is we've spent a fair bit of work on doing a whole bunch of loss assessments, or I should say Tim Sullivan and his team did. And for that particular pathway, if you limit your building drift to 0.5% or less for your damage control limit state event, you should, in most cases, expect to meet those losses. There is an ability to be more flexible than that, but you need to do more work, and I can show you some of that work separately if you want.
That's 4.5% or what return period?
Either 250 or 500.
Any more question? No? Okay.
Sorry, I did have one, if that's okay.
Yeah, sure.
Just, I'm interested in why we're narrowing down so much just on deformation limitation. I understand that there are a lot of components in certain building types that are force or acceleration sensitive, and so I'm not sure how much analysis has gone into the fragility of those acceleration sensitive components.
Again, I might hand over to Tim and or Stu to kind of comment on your question.
I think there is more research going on. We have looked at, as part of those loss studies, you know, the impact of design for smaller drifts and accelerations and losses. And there are some building components that, for example, lifts, some mechanical electrical equipment that even if we brace them, the mechanical electrical equipment will still lose their functionality, and so there's costs and so on associated with that. But at the moment, I think there's enough evidence to suggest that even though you do, and we do then try and design to brace and protect the acceleration sensitive equipment more, so as part of this process, you look at both, of course, limiting the drift, but also bracing your non-structural elements for potentially higher forces. And so through that process, we are seeing reductions in losses, but there are some parts of our buildings that, if you're in a region of high seismicity like Wellington, we're just starting to see that actually you're still going to have high losses. So even if you do this, and there's maybe Stu wants to add a bit more in terms of clarifying what we're sort of doing about that.
Yeah, so I mean, one of the outcomes from the loss studies was that if you're in a high seismic zone like Wellington, simply bracing everything up and making a really stiff building doesn't really work. Sorry, I'm not quite sure where the person asked. Oh yeah, it doesn't really work, and so we've introduced some peak floor acceleration limits for the higher performance buildings, which effectively means that you either do a whole bunch of seismic verification of your acceleration sensitive equipment, or you adopt base isolation or viscous damping to get your floor accelerations down. And if you see what's happening in the Wellington market already, most of the higher performing low damage buildings are isolated or they've got supplemental damping. So we don't think it's too onerous for us to sort of go down that pathway.
One more question. I think it's the time to wrap up this session and move to the next one. I want to just say thank you to all of the presenters for the amazing presentation. Please join me.